In this unit, we have categorized the topic of solution into three: solute, solvent, and solution. In solution, there are three categories that we will look closely into: strong electrolyte, weak electrolyte, and non-electrolyte. In this particular video, we will focus on the topic of solution, mainly the strong and the weak electrolyte. So let's begin. Let's compare the strong, weak, and the non-electrolytes to review. The strong electrolytes are those who are able to conduct electricity. And these are substances that, for example, sodium chloride, that can dissociate 100% of the time when submerged in water. So you see, for example, if I were to have sodium chloride here, and when that solid is submerged in water, it splits off or dissociates into two. Not just few of them, but all or most of the sodium chloride would dissolve in water like in such way. In a non-electrolyte solution, we have something like methanol. When it's submerged in water, they do not dissociate, meaning it does not split apart, but just remain intact. It still dissolves, but just stays intact, and that prevents an electrolytes to form, and so therefore there's no conductivity in electricity. So you see no light bulb occurring here. Weak electrolytes are those that are just like the strong electrolytes, but not all of them dissociate, less than 100%, 20%, 10%. So you see the dim light there. But our main focus is on strong electrolytes. So how do we know if some substance is a strong electrolyte? What kind of categories do they fall under? Well, strong electrolytes are from soluble ionic compounds. Ionic. So here I have an example of ionic compounds: lithium nitrate, calcium sulfide. How do I know these are ionic? These are ionic because there's a metal and a nonmetal. Metal and nonmetal. Now, how do I know if they're soluble? We have to look at the solubility chart, which is also located in your reference sheet. Now, in the solubility chart, can you find something that has lithium and or a nitrate? So if you look on the right-hand side, you see the nitrate over here. And under nitrate, you see that it is soluble. So anything that has nitrate in it is going to be soluble. So when this solid is submerged in water, what will happen is you have lithium that has been split off into lithium plus, and AQ representing that it is hydrated by water, and nitrate in ionic form. And so this lithium nitrate has been dissociated in all of them because it is considered to be soluble. So I'm going to write this as soluble. What does that mean for the electrolyte? Well, this means that this is therefore a strong electrolyte. What about calcium sulfide? Calcium sulfide, anything to do with calcium or sulfide over here. Do you see it? Hopefully you're able to see that sulfide on the right-hand side. You can see that it is under insoluble compound. And also, if you look at the exception, it doesn't fall under the exception. It is combined with group 1A ions or ammonium ion. And calcium, it does not fall under that. So therefore, sulfide, anything that has sulfide with this, other than it has a group 1 ion or ammonium, it will be insoluble. What does that mean when it's submerged in water? Well, it's not going to form an aqueous, nor is it going to split. It's going to remain as solid, intact. In fact, this wouldn't be a nice homogeneous solution. You'll see a separation between the water and the solid. So this is considered to be insoluble. So what does that mean for the electrolyte? So therefore, not an electrolyte. So you try this learning check. It says which of the following can form a strong electrolyte, and come back and check the key. And here is the key. So far, we have covered that a soluble ionic compound can form a strong electrolyte. There are two more. One is a strong acid. Strong acid are able to form a strong electrolyte. For example, these are some of the strong acid. HCl, hydrochloric acid, is ability to split in water or dissociate in water. All of them or most of them will dissociate in water. Nitric acid, sulfuric acid, you can see that they have split in its aqueous form. Now, how do we know if something is a strong acid? We can know by looking at this chart. This chart is also in your reference sheet, and these list all of the strong acids here. If it's in this list, then we can say that it is a strong acid. If it's an acid but it's not on this list, then we can automatically assume that those are weak electrolytes or weak acid. Now, how do we even know that it's an acid to begin with? Well, there are two categories. One is that you will see that there is a nonmetal and a nonmetal. So H is a nonmetal, Cl is a nonmetal, H and O, they're all nonmetals. Second component, and it's one of the most important component, you see that the hydrogen are written in the front of the formula. It's not always the case, but for an introductory chemistry course, you will see that the hydrogen will be on the left-hand side. So that's how you know that this is an acid, and then afterwards you determine it's a strong acid by looking at this particular chart. There's another category that allows strong electrolytes fall under, and that's strong base. Strong base example is here. You see potassium hydroxide forming into potassium ion and hydroxide ion. They split all of the dissociate. So that dissociation allows this to conduct electricity, and so therefore this is considered to be a strong electrolyte. Well, another question would be, how would I know if this base is a strong base? Again, in this chart has strong acid and strong base. This chart on the very right-hand side, all of the metal hydroxides are considered to be strong base as long as they're on this list. Please be careful on the heavy group metal 2A hydroxide. This is calcium hydroxide, strontium hydroxide, barium hydroxide. So if you look at the periodic table, calcium, strontium, barium, and below, those are all strong. But magnesium hydroxide, that's above the calcium on the periodic table, that wouldn't be a strong base, hence not a strong electrolyte. The question then again is, how can I tell it's a base, right? This one's a little more challenging one. There's no H in the front and the H is in the back. That's not the main case, but you will see that the hydroxide, OH minus, will be formed when it's submerged in water. And this comes with a little more practice on how to see that, and that will come more later in your future chemistry. Now, I would like to dive into the weak electrolytes. So this is the one in the middle. So this is when a substance, when in going into solution, they're going to only allow small electrical current in that solution. And that's because not all of the component will dissociate. So you see there's substances that are still remain intact, and over here you see that some have been split off, so there is a light dim light bulb on. So one category under weak electrolyte is a weak acid. So I've said if it's not in the strong acid, then it's automatically weak acid, and these are some of the common weak acid you might see that you could read on your own. But what I do want to illustrate is one of them is the carbonic acid. So this is a carbonic acid, and when it's submerged in water, it will split off into two. When it splits off into two like this, the thing is, it can have the ability to recombine and reverse back. Okay, so in fact, not all of the H2CO3 will dissociate. So this image shows here's a carbonic acid coming in, and you see HCO3 minus. That's because it's been split off. That two, there's no longer two, but it's one now. The other hydrogen left. But there are still the one in the green blob. It shows that it still remains intact. So this shows the weak acid. This is a weak acid, hence the weak electrolyte. Then there are weak base. The weak base, here are some common weak base that you see on the very left-hand side in this table. And here I have shown an image. You see how this is ammonia is considered to be a weak base because when mixed with water, it has the ability to produce hydroxide. So remember, OH doesn't necessarily have to be with the base, but it has the ability to make that water into a base. But the thing is, if you look at this arrow, it's showing that it's also going in a reverse direction, meaning that this could orient itself to form ammonia and water, back to water. So when submerged in water, here you see the ammonia all stays sort of intact. Only few allows ammonia to form ammonium, which is that positive charge, and then water to form hydroxide. So not everything that gets dissociated, and hence this is a weak base. This is a good point to do a learning check. I will do 2 of them and you try the other 2. So let's target sodium hydroxide. Sodium hydroxide, I notice that there is a hydroxide there and there's no H in the front. So automatically I know that this is going to be a base. So I'm going to write base. Was it a strong base? So I look in this chart and it does fall under strong base because it's a sodium hydroxide over here. So I'm going to write strong base. Well, if it's a strong base, then this is definitely a strong electrolyte. Let's try HF. Non-metal, and we have a hydrogen in the front. So therefore, I can assume that this is an acid. So is this a strong or a weak? So I look in this chart over here. HF is not in one of the categories, so therefore this is a weak acid. So therefore this would be a weak electrolyte. All right, now you try the other 2 and come back and check the key.